Okay, now 5 minutes in. Yeah, so this is the third reaction on number 1. And if you go through the flow chart, I'll sort of explain how I got to the product. All right, and then what I'm asking you guys to do is get to the mechanism. So as you look at that one, is there a leaving group? You're always going to start there, and there is. So we can do substitution. If there's a leaving group, you can do substitution. Is there a beta hydrogen is the next question, and there is. We've got several here. All right, there's a beta hydrogen there, and there's 2 there. So we can do elimination. All right, now, is there either a strong base or a good nucleophile? All right, and this is really the critical juncture. All right, if you have a strong base or a good nucleophile, you're going to do E2 or SN2. If you don't, you're going to do SN1 or E1. And so that's the one you want to make sure you can identify. All right, and so all we've got is water. We've got a temperature there. Okay, water is not a strong base or a good nucleophile. Methanol's not. Ethanol's not. Think about water. Keep in mind that water is not a strong base or a good nucleophile. It's not a strong acid. All right? You drink water, you play in water, you swim in water. If it was a strong base or a strong acid, you would know it. So that means any neutral oxygen is not going to be a tremendously strong base or good nucleophile. All right, so from there, the answer is no. So now this is going to be the SN1 E1 path. Is the leaving group on a tertiary or benzylic carbon? It's not. It's a secondary, and it's not benzylic. All right. Secondary, the carbon that the halogen is on is bonded to 2 carbons. And that carbon is not bonded to an aromatic ring or a double bond. So is the leaving group on a secondary carbon? Yeah. So now SN1 or E1 is possible via the carbocation. It's going to be slow. It's going to be best in a polar protic solvent. We went through solvent effects at the end of the last class if you haven't seen the video. And so we can do SN1 or E1. And now figuring out which one that is comes down to the temperature. All right, you should not look first at the temperature. You should never look first at the temperature or the solvent. The solvent is not going to tell you what kind of reaction happens. The temperature is not immediately going to tell you what kind of reaction happens. You can have an SN2 at a really high temperature. You can have E2 at low temperature. The temperature only helps once you're down to its S. It could be S or E. It could be both of them. And in that case, a lower temperature will favor substitution. All right. And so I've drawn a substitution product. OH substitutes for Br. Right? The OH comes from water. Now, the tricky bit is things have rearranged, right? So the leaving group was on a secondary carbon that wasn't bonded to the benzene ring, and now the thing that came in, the nucleophile, is bonded on a tertiary carbon next to the benzene ring. So go ahead. I know you've had, some of you have had like 12 minutes for this already. But I'm going to give you a couple of more minutes to try to draw a mechanism for how this reaction happens. It is an SN1 reaction. Bless you. if you've got your mechanism down, the next reaction will be the second one, the upper right on number 2. Okay, so on the mechanism. My phone's talking to me. What is the first thing that happens? Right. If it's an SN1 reaction, the leaving group leaves. All right. That is going to be the classical first step of either the SN1 or the E1. Get a carbocation. Any stereochemistry is now lost. Right? That bromide, which initially was back, is gone. That carbon is no longer chiral. It's sp2 hybridized. It's trigonal planar. There's only 3 things attached to it. Right? So even if the Br came back on, it could come back on from either side. So it wouldn't have to come back in the same way. So I see a couple of people hanging in. Like, if you're interested in thinking about that, this is something that, and it gets very complex. Like, you think about this molecule surrounded by solvent. Right? The bromide pops off. If there's nothing else around that can happen, the next most likely thing is the bromide just comes back on. Now, does it come on same direction or behind? And how you tell, really, it could come on from either side. But in reality, it depends how far away it goes. Right? I don't know if anybody ran away as a kid, and I'm not trying to pry. I ran away a bunch of times. Like, got as far as maybe 2 houses down. Went back. I doubt my parents know. Right? That's not really, nobody, like, if you ask my mom and dad, did Paul ever run away? No, of course not. In my mind, though, I was gone. Okay, so bromide pops off, but it doesn't go out into the solvent, right? It just kind of gets a little farther away, and then it comes back on. When that happens, it's more likely to come on from the same side. But if it goes away, and then solvent gets in between the two, right now it really is lost, right? It's just out. It's like if I had gotten on a bus. I'm gone. So if the bromide gets out into solvent, now it can come in from either direction pretty much equally. All right? So there's a lot going on in this. We really only look at this when there's a solvent that can do a reaction. Okay? This process, the bromide leaving, is slow. So like I said, if you've got hydroxide here, hydroxide is just going to come in and do the reaction. It's going to drive the reaction. Relying on the bromide to leave and get far enough away for solvent to do something is a slow process. So once that happens, right, we got a sea of water here. I'm just going to draw one of them. But that water could come in from the same side. It could come in from the reverse. So it's important, once you get down that SN2 gives you inversion, right? So if we were using hydroxide here, and this was an SN2 reaction, the hydroxide has to come from behind here and kick out the bromide. That would mean, in this case, the hydroxide would come from the front, kick the bromide out the other side. If the bromide leaves first, the water can come from the front or back. All right, so the best way to show that is either with, well, let me draw it. All right, so there we go. Water attacks the carbocation. I'm going to end up erasing this in a minute anyway. All right, so really I think the best way of showing that is just to draw a bond to that O. Just a simple line, not a wedge or a dash. If an atom is chiral and you don't show any 3-dimensional shape to it, The assumption is it's either a mixture or a 50-50 mixture. All right, you could also draw it. Sometimes you'll see people draw a little squiggly line there. That's kind of more, that's explicitly telling you this is a three-dimensional atom, and it's got some front and back. The most cumbersome way to do this would be to draw both of them. Sometimes you'll see people add to either the squiggle or the line, like racemic. Doesn't really matter. I here am usually going to show, like I've shown up here, I'm just not going to show any stereochemistry. All right, so that would be the straight up SN1 process. Does that explain the observed product? It doesn't, right? So I wind up with the O and the same carbon as the Br, should be there. And the benzylic carbon in my mechanism, nothing's happened there, right? So that methyl should still be back. So this is wrong. And water did not do that. So what happened? And why? And why did it do that? Yeah. So what happens here? All right, I haven't been drawing that H. I've just been drawing the line structure, right? Assume the H. So that hydrogen, that hydride formally moves over. This H takes these electrons and moves to the carbocation. You're still going to have a carbocation after that. All right, so it's still a reactive intermediate, but you have a much better cation. And again, when I say better, I mean more stable. All right, now there's two hydrogens there, so that carbon, the carbon that had the bromides, no longer chiral. We don't have to, and it's not going to do any more reactions. It's sp3, it's got a couple of hydrogens. So we go from a secondary localized cation to a tertiary delocalized. I'll get out of the way in a sec. And I'll stop. I feel like I'm not doing my job very good today. I'm feeling down. They teach you when you start teaching, you know, not to ever like talk into a corner like that. I feel like I can get away with it. I have a microphone. You can go hear what I had to say later. But they also tell you not to wear a mask. Okay, so you go from a secondary localized cation, right? The bromide leaves, the carbon it was on is positively charged, doesn't have a full octet, and it's secondary. So it's only drawing sort of stabilization from 6 sigma bonds around it. By undergoing a transition to a tertiary cation, now I've got 9 beta bonds to donate electrons in. And more importantly, one of these is a pi bond, right? You can actually draw resonance structures where you move the positive charge around the benzene ring. So these two positions and the position directly across the ring bear significant partial positive charge. All right, so this is way more stable. And now, what we did, now to get that OH there, that cation is, you know, like I said, in a sea of water. So the water is just going to attack the cation. And again, that is a carbocation. By this time, the bromide's long gone. That carbocation is planar. Attack can come from the front or back, top or bottom, doesn't really matter. And it's important, water is the nucleophile, not hydroxide. Hydroxide's a really strong base. It's a good nucleophile. Hydroxide would be doing an SN2. And there's nothing in this mixture that can make hydroxide. You don't have any kind of base that can pull a proton off water. So there's no base strong enough to pull a proton off water. But now, this is not water anymore. This is now an oxygen with 3 bonds. got a formal positive charge. Those protons now have a really strong partial positive charge. So you've got another water, and that will take the proton to get us to the product. I want to bring some attention to this water right here. All right. A lot of you, maybe I'd be lying if I didn't see some confused looks, inquisitive looks. I hope nothing's like super unknown there, but there's a lot. There's a lot going on in this reaction. But one thing I want to point out is, just because I've written one water here, this is not a balanced equation, all right? Water is the solvent. You have a ton of solvent relative to the molecule in it. All right, so you've got as many water molecules as you need. So water is a nucleophile here, then it's a base here, and all the while, these molecules are surrounded by water. All right, so you've got plenty of water to do all those steps. And then the stereochemistry, so I've drawn a single enantiomer over here. This molecule is also chiral. Right? There's one chiral center now, and you get a racemic mixture. Questions about that one? Okay. So go to the one on the board on the right there. I want you to tell me which one of those two reactions is fastest and what the mechanism is. SN1, SN2, E1, E2. On the handout, obviously I'm drawing them as proper reactions. I'm being lazy here. I'm basically saying both substrates are treated with the same reagents. Another couple of minutes on the one on the middle board, and if you've got those, you can work on the other two. All right, on this one in the middle, let's do reaction type first. So, do you have a leaving group? Both molecules have a leaving group. Do you have beta hydrogens? Clearly you do. Do you have a strong base or a good nucleophile? What is the strong base or good nucleophile? Yeah. So, potassium T-butoxide. We've got potassium T-butoxide and we have methanol. It's kind of a strange mix. And it's because I wasn't looking at what I was doing. Normally, you would make, if this is too much, I'm not going to ask you about this, but normally the way we would make, so to make this one, you would use potassium metal. So I would take my alcohol, in this case I would take T-butanol and potassium metal, and I would mix them. You guys have all seen, I hope, videos of people throwing sodium into water, potassium into water. I'd love to do this for you. They don't let us do this in our brand new building. We used to do this in the old one. It's kind of why the old one was such a crappy building. This undergoes a redox reaction, so the potassium gives an electron to the oxygen, right? And this is going to cause that, basically we put an electron here to get an O minus and an H dot. Two H dots combine. And you get hydrogen. All right, this is a really exothermic reaction. So the fire you get from sodium and water, sodium gives away an electron to water. You get sodium hydroxide and hydrogen and a lot of heat. Generating hydrogen gas and heat in the presence of air is a bad thing to do unless you want fire, in which case it's an excellent thing to do. All right, so it bursts into flames. It's very fun. Potassium is more reactive. As you go down the periodic table, you get more reactive. You can add lithium to water, and it fizzes a little bit. No big deal. Sodium usually bursts into flames. Potassium will. I've seen people blow up beakers pretty easily with that. You always want to do that demonstration in a non-shatterable thing. Cesium, you can like blow up a bathtub. Fun stuff. Anyway, so this is weird. Normally, you would see potassium T-butoxide in T-butanol, because that's how you make it. But you could do it. You could isolate the potassium T-butoxide and then put it in methanol. It would be weird. This really doesn't add. This is color commentary, all right? So look up those videos if you're not sure what I'm talking about. It's fun chemistry. So the base here, though, the thing I really ought to be emphasizing rather than blowing up bathtubs is you've got K plus and a localized O minus. Methanol is you can't drink methanol. Methanol is poisonous. It really irritates your skin if you swim in it. But it's not a strong acid or base. All right? You can, in fact, drink methanol and not immediately die. All right? Unlike a strong acid or base. Methanol's effects are more, they're not even chronic. They're more metabolic. You have to metabolize the methanol for it to do any damage. Unlike, like if I drink a strong base, it just dissolves my tongue and my esophagus and all that, right? So it's a much more acute, quick thing. So methanol here is a weak base, weak nucleophile. And I just want to, again, point out that the methanol, the carbon is covalently attached to that oxygen. Methanol, ethanol, any of these alcohols, you did not have a hydroxide there. Right? That's not an OH minus. So it's not a strong base. So this is a strong base up here. Methanol is a weak base. So in a reaction where a base is needed, T-butoxide is going to be the one to react. T-butoxide is not a very good nucleophile. And I've told a bunch of you, I should try to bring my computer in. Maybe I'll record a little PowerPoint. Like if you look at the space filling model, it shows why T-butoxide is not a very good nucleophile. That O minus is sitting next to a whole bunch of mass. All right, that T-butoxide, you can freely rotate around the CO bond, but you're always going to have a methyl there. All right, so t-butoxide is a much better base than nucleophile. Okay. So you do have a strong base or a good nucleophile. So we're going to go yes, and that's going to end up with, if I asked you to predict the product of this reaction, you would arrive at the conclusion that this isn't going to be an SN2 or an E2. Right? We've got a primary halide, so SN2 can happen here. We got beta protons, so E2 can happen. Probably you would end up predicting this would be an SN2, right? Low temperature, it could be SN2 or E2. But what is this reaction? It's an E2. And the way you know that is there's an alkene at the end, all right? So I want to keep, there's sort of two approaches to some of these problems, and it's this way with science as well. There's discovery science where we're, mix a bunch of chemicals and see what happens. You can make a prediction. You should make a prediction if you're doing science. Right? I have a hypothesis that this mix of chemicals will do this. You mix them together, you see what happens. Were you right? Were you wrong? There's another approach where somebody else mixed them together and we notice that we get this and we got to explain it. All right? If I give you the product, right? If I give you the starting materials and the reactants and the product, I am not asking you to predict what happens. I'm telling you what happened. And your job at that point is to tell me how it happened. All right, so here, you look at this, you don't have to go through the flow chart. We got a strong base. We do an elimination reaction. Strong base with an elimination reaction is going to be an E2. And that's to tell me the mechanism. You don't even have to do all that at this point to answer the question of which one is faster. All right? Where is the one difference in the two reactions? The leaving group. And again, this is a scientific method, right? The best way to do any experiment is to change one variable. And this extrapolates into these kind of questions. If I had given you the chloride, sodium hydroxide, and water gives the alkene, and the iodide and t-butoxide and methanol gives you the alkene, you couldn't really say which was faster, right? You've changed the solvent, you've changed the base, you've changed the leaving group. With a lot of experience, I could tell you which one I thought would be faster, but that's not proof, right? Experience and prediction based on empirical observations, we should listen to it, but that is not definitive proof something's going to happen. So in this case, we set it up nicely. Implied here is sort of same concentrations of t-butoxide and starting material, same temperature for both reactions. The only difference is in one case the leaving group's a chloride, and the other one the leaving group is an iodide. So which reaction's faster? The iodide. The leaving group ability improves as you go down the halides. All right? Fluoride is never a leaving group in chapter 7. The carbon-fluoride bond is really strong. So even though F- is really nicely stable, breaking that really strong bond is hard. The carbon-chloride bond is a little stronger. Sorry, it's a little weaker, and you can break it, but it's still decently strong. The bond strength between carbon and halide decreases as you go down the periodic table. So iodide of the halides, iodide's the best leaving group, and when we say it's the best leaving group, we mean it's it will react fastest. So that one's going to react the fastest. Like I said, not trying to beat this horse too much. You can say that when everything is the same except the one difference, right? So if I change the leaving group and I change the base, who knows? Yeah.
Do elimination reactions favor bases more? How does that work?
Favor what?
Like elimination reactions, do they favor bases more, and like substitution favors nucleophiles?
Well, so yeah, if it's E2, so this is, this is going to be an elimination because there's an alkene, okay? So then it's E2 because there was a strong base. SN2 and E2 are alike in that E2 happens when you have a strong base, SN2 requires a good nucleophile. There are a lot of molecules that are both.
So if it's just a strong base, will that nucleophile?
Yeah, yeah. So t-butoxide does E2 better than it does SN2. That is not a guarantee, right? Like asking you, this would be a, nearly use slang there. Semester's getting away from me. This would be a cruel thing to do to you as a question, like predict the product, right? Because everything on the board in that flow chart suggests this would be an SN2. And in fact, it might be an SN2. I've seen t-butoxide do SN2 reactions. It's just not real good at it. It very commonly does E2. Okay, so let's do these two. Do the top one first, then we'll do the second one, but if you've already got the top one, we can do the second one. And again, you're kind of looking for what is the one difference, and then you need to know, like, what does that difference mean? Yeah. Yeah, sure, I can draw the mechanism for the E2. I'm going to draw it below here. All right, so I got t-butoxide and iodide. You're going to make the double bond between the beta carbon and the alpha carbon by abstracting. Tell you what, I'm going to draw the iodide differently. All right, so the t-butoxide attacks the beta hydrogen, beta proton. This makes the OH bond. So one of the things we're going to get is t-butanol. The CH bonding electrons make the pi bond, and then the CI electrons go to the I. So there are your three products. I mentioned in class on Tuesday, I think, that the E2 is irreversible. All right, the E1, and we'll do an E1 here in a bit. The E1 is reversible. Right? The leaving group leaves, and then the leaving group or the solvent grabs the beta hydrogen. You generate a strong acid, and a strong acid can add to an alkene. So the E1 tends to be reversible. In the E2, right, we get an alcohol, weak acid, weak base, alkene, perfectly stable, and the leaving group, which is going to be, by definition, a weak base. Right? So you get a whole bunch of stable reactants. So the E2 happens, and that's it. I've also redrew the iodide here just to emphasize to you, because it isn't always important, and it wouldn't be wrong here if you had left the iodide down like this and drawn the arrows. That wouldn't be an incorrect mechanism. But just keep in mind that the beta proton that gets grabbed has to be anti to the leaving group. Is that? All right, another couple of minutes on the top one there. All right. So what kind of reaction is this? It's an SN1. What are all the ways you know it's an SN1?
You don't have a strong nucleophile.
Right?
Low temperature. Those are the two I'm thinking off the top of my head. Oh, also like the leading group switches.
Yeah, leaving groups tertiary. There's one more thing that would give an SN1 away. Sorry?
We can see the product, I guess.
What about the products?
We can see them, so we know it's
Okay, yeah, but there's something about the products that will tell you that this is an SN1. It's racemic, right? So I've shown one configuration for this chiral atom. If this was SN2, it would invert. So, right, the biggest one, there's no strong acid or base. Sorry, there's no base or strong nucleophile. No strong base or good nucleophile. Leaving groups on a tertiary atom, it's a pretty good sign. And then we lose the stereochemistry. Okay, so it's SN1. So which reaction's fastest? How come? Right. So, yeah, sorry, I cut you off there. You get a tertiary cation either way. Like, both of these reactions would probably go by SN1, and pretty decently. So sometimes I do these. And again, this is one you'd have to do some lab work. The difference in rate for the two over here is really incredible. Okay, the iodide would be done. You'd get everything set up. You'd pour your potassium T-butoxide in it. And by the time you could like get around to TLCing it or getting an NMR, like the reaction's probably done. The chloride would probably need to go overnight. Right? It's a big difference in rate. These two, they're both pretty fast. But one is significantly faster than the other. So you're going to get a cation. All right, there's your carbocation. That's the cation we'd get from the top one. And the cation from the bottom one would have this double bond that could stabilize by resonance. All right, so the cation you get from that bottom reaction is a good bit more stable than the one you get from the top reaction. And because it's SN1, and this is true for E1 as well, the rate limiting step is making the cation. So if you increase the rate at which you make the cation, you increase the rate of the reaction. So SN1, E1, the better the cation you make, the faster the reaction it is. Leaving group stuff still applies here. So if we had the same structure, but say this was a chloride, like if they were both benzenes and that was a chloride, the bottom one would be faster. If we had these exact structures and the top one was chloride, well, that would still be. You'd have two factors there that would say the bottom would be faster. If we had a chloride on the bottom and a bromide on the top, you'd be hard-pressed to answer that. Yeah.
So I kind of looked at it like there'd be more stability with the benzene, and that would slow it down because it'd be less reactive.
So so the benzene and this it's a good point, and a lot of students see this in the beginning. So the bottom molecule is more stable than the top molecule. And yeah, logically then you'd say, well, that should make it react slower. Like if something's more stable, you'd expect it to react slower. But the difference in stability between these two is a lot smaller than the difference in stability between the cations. Right? So as we look at right, we sort of start there. We do that, right? So yeah, the benzene molecule is a little bit more stable. The cation you get with the benzene molecule is much, much more stable to not make it quantitative. But does that make sense? Okay. Good question. Any others? All right, take a couple of minutes on the bottom reaction here. I guess I should circle. case people are watching on mute at home. If you have an answer for the bottom rate question over there, try this one in the middle here. All right, on the one over here on the lower left, what is the mechanism type? SN1, SN2, E1, E2. Got to vote for E1. It's E for sure. There's an alkene, right? You lose a leaving group, you get an alkene. That's an E. That one is E1, yes. What about this one? So the question is, do you have a strong base or a good nucleophile? Yeah. So magnesium hydroxide. Magnesium hydroxide is a miserable compound. All right. Magnesium salts, calcium salts tend to not be soluble in anything, especially the hydroxides. I don't know if do they still make you guys memorize solubility rules in Gen Chem and AP? Man, you guys. Yeah. I'm gonna find a hill that's uphill both ways and make you run it. It's fine, but you guys know do you know magnesium? Probably don't know magnesium, but you know calcium, and they're kind of related on the periodic table, right? Yeah, they're right next to each other. Good. Anybody? I have never been. This is dangerous things to talk about. I have never been in a Wake Forest dorm shower. Okay. That out of the way. My guess is most of them, except maybe the very newest ones, have a bunch of white crap on the shower heads. Is that true? Yeah. Those are calcium salts that like come out of the water. Calcium salts tend to be really insoluble. All right, magnesium sort of the same way. All right, so this would be a terrible reagent to use for this. However, I just get bored writing the sodium and lithium and potassium over and over and over. So magnesium hydroxide is a base. It's soluble enough. You'd get some hydroxide up in the solution. So you've got a strong base. Again, magnesium 2 plus OH here. So an OH bonded to a carbon is that oxygen's neutral. It's a covalent bond. An OH bonded to any kind of metal is going to be an OH minus. So you've got a strong base. So this is going to be an E2. And again, you would predict this. You've got a leaving group. You got beta hydrogens. If you came to the conclusion that you had a strong base, you'd be SN2 or E2, and then the temperature's high. But again, you don't have to do this. I've given you the product. The product's an alkene. So it's an E2 reaction. At least one of them is. So what's the fastest of these two? You say the top? Yeah, I think it is. So what you have to do is you have to think about this as a chair. And it's not a perfect chair. All right, so the chloride is up. Up here is going to be axial. And then the methyl is also up. All right, so there's your CH3. And that means the axial position on that carbon is an H. All right, why did I draw it as a chair? Yeah, I'm looking to see if they're anti or not. Okay? So if it's an E2 reaction, the proton that gets grabbed has to be anti to the leaving group. In a ring, that actually means the proton has to be trans to the leaving group. All right? So in a ring like that, the reaction is going to be, an E2 reaction will be a lot faster having a proton trans to the leaving group than syn or cis. All right, so the top reaction is an E2. But if you look at this proton is the only beta proton. All right, which means you have to grab that proton. In order to make an elimination reaction happen, that's the proton that has to be grabbed, and there's no way to make that proton anti to the leaving group. Right, if you do a chair flip over here, well, so hang on. Fumbling. So that one's on the top. All right, so this H here is gauche to the chlorine. If I do a chair flip, it's still going to be gauche to the chlorine. There's no way to make that H anti to this chloride, which means that H cannot be involved in an E2 reaction. All right, that's going to make it slower. E2 is always faster than E1, but it means this bottom reaction, if it goes to that alkene, has to be an E1 reaction, even though you've got a strong base. Let me write some stuff down here. So E2 is faster than E1, but the proton in the E2 reaction that gets abstracted has to be anti-coplanar with the leaving group. All right, the E1 reaction, there are no stereochemical restrictions on that beta proton. So if there's a proton beta to a carbocation, it can be abstracted. All right, so we've already established that this one over here is an E1. So draw the mechanism for that and draw the major product. And if you've drawn if you've drawn what you think is the major product, draw all the products. And then we'll do the number 3 on the worksheet. All right, so I'm going to take you through the mechanism on the E1. Again, it's E1, so the first step is the leaving group leaving. This looks a lot like the first molecule we did today. All right, we got to it being an E1. There's a leaving group. There are beta protons. Leaving group's secondary. There's not a good nucleophile or a strong base, right? Ethanol is going to be a weak nucleophile, weak base. So the leaving group leaves. Ethanol is going to come in and do something. Ethanol could attack as a nucleophile, but the temperature is a little high, so we're going to, if you've got SN1 or E1 possibility, higher temperature, you're going to tend to lean toward elimination. All right, so you've got beta protons here and here and here. And again, once you have that secondary cation, and you might be wondering, why don't you do migration? You probably do migration. Okay, so just like the last time, I've covered it up, I guess. So if this migration, secondary, a proton, this cation is exactly the same as what we just made. Yeah, this cation is what we made over here. If we get a migration at 20 degrees, we certainly get it at 30 degrees or at 78 degrees. So we end up with this tertiary cation. And now we're going to lose that beta proton. Let me draw that better. Hang on. So we have neutral ethanol. We don't have ethoxide. We don't have hydroxide. We've got neutral ethanol. Yeah.
On the one over there, you have the orange family, like by a lot. To the arrows,
Yeah, yeah. No, that, I mean, sure, that definitely would happen.
but would you, in comments, ask them what's
If I asked you explicitly, like which side's favored, you'd need to be able to tell me, yeah. But if you had just drawn equilibrium arrows like that, that'd be fine. All right, so the ethanol is going to act as a weak base to take that beta hydrogen. The beta hydrogen is going to make the pi bond. Now, that pi bond could be cis or trans. All right? There are no stereochemical restrictions on grabbing the beta hydrogen. So you can grab either of the hydrogens and you can make both double bonds. So what do I mean by both double bonds? And there's 3 carbons here. 3. So you could get both of those alkenes. Top one is going to be major, bottom one's going to be minor. I would never ask you to predict like how much of one. Like you don't have to tell me that's a 78-22 mixture. You just need to tell me one's more stable than the other. All right, so on the top, what I've indicated there is the major product. It is the major product because it's the most stable. Okay, you've got the 2 big groups on each carbon trans. Big group on this carbon is the phenyl. Phenyl's bigger than methyl. On the second alkene carbon, propyl is bigger than hydrogen. And like I said, this ends up being reversible because the other product you get is a strong acid. You get ETOH2 plus, chloride minus. Right? That's essentially HCl dissolved in ethanol. So go back to your chapter 8 stuff. If I had said, here's an alkene and HCl and ethanol, you guys would probably draw me a product where HCl adds to the double bond or HCl catalyzes the addition of ethanol to the double bond. All right, so E1 is reversible. And what happens, that means all these steps can reverse. And that's why anytime you have, let me try to draw this a little more generically, because this is kind of an important chemical principle. All right, anytime you have a situation like this, all right, I have some molecule A and it's in equilibrium with B and it's in equilibrium with C. What that means is B and C are also in equilibrium. All right? Like B and C may not be able to directly go back and forth the way I've shown with that green arrow, but they can go back and forth through A. All right? So as long as everything is in equilibrium, then everything is in equilibrium. You can't say, well, this, like the only way you could say this wouldn't happen is if, say, A to C could not go backwards. If A to B happens reversibly and A to C is irreversible, you eventually just end up with C. But as long as both of these reactions are reversible, then B and C are in equilibrium. And so any 2 things in equilibrium, you're going to decide how much you have based on stability. The major alkene is more stable than the minor alkene. Questions? All right, take a couple of minutes if you haven't already and work out the mechanism on this bottom reaction. Before I start talking about the mechanism, do you have a strong do you have a strong base or a good nucleophile? What is it? Right, yeah. So this one's both a strong base and a good nucleophile. This probably doesn't look immediately, well, let me ask you this. Do you have a leaving group? Well, something happens, so maybe. Like, you probably shouldn't look at this and decide. I would find it a little strange that if you looked at this and said, yeah, definitely, I have a leaving group. But I've shown a reaction happening, so something has to happen. And actually, localized O minuses are hardly ever leaving group. Like seriously, they're never leaving groups. All right, hydroxide's never leaving group. OCH3 minus is never leaving group. There's one exception in this kind of chemistry, and that is with an epoxide. All right, so if you go back to chapter 1 or 2, there's a whole lot of ring strain here. And that means that that CO bond is weak. All right, so again, I'm not going to directly, like epoxide chemistry is covered in chapter 8. You can make, you can turn an alkene into an epoxide. You can do an acid catalyzed ring opening. That reaction might ring a bell. Like you protonate the O in the epoxide, and then water can attack the epoxide, open up the ring. This is the base version of it, right? So the epoxide, we can't protonate this because there's no acid here. We got strong base. If you've got strong base, you're never going to have a strong acid in the same mixture. Okay, so that's sort of the background, just thinking about these molecules, what do they do? Now look at what gets formed and what gets broken. Right, we make a new methoxide carbon bond. That OCH3, the O in the OCH3 makes a new bond to carbon. And we break a CO bond. Right? And then we make an OH bond. So those are the three things you have to do. You need a curved arrow that makes a bond between the O and the methoxide and a carbon. You need an arrow that breaks the CO bond in the epoxide, and you need an arrow that makes an OH bond. So your mechanism needs to have all that and nothing else. Figuring out the order is important. Like I said, under base catalyzed conditions or under basic conditions, you're not going to have any strong acids. So we're not going to make the OH bond first. You could imagine breaking the CO bond before you do anything else. But if you do that, you're going to end up with a primary carbocation and an O minus. That's not very likely to happen. Right? This is not such a good leaving group that it just like leaves and gives an a strong base and then a bad cation. So the next logical thing would be, since you have you do have a strong base in a good nucleophile, it's going to be more like an SN2 reaction. Right? So the SN2 is driven by the nucleophile. Here, this reaction is going to be driven by the methoxide. So methoxide will attack this carbon. How do I know it's going to be that carbon? Well, when this reaction happens, it's driven by the nucleophile. The nucleophile is going to attack the less substituted epoxide carbon. But you didn't know that. Like if I had asked you to predict that, that would be unfair. You know it attacks this carbon based on the product, right? So methoxide attacks this less substituted carbon. Carbon can't have 5 bonds, so the weaker epoxide CO bond now breaks, gives electrons to the oxygen, you get an O minus. And what drives that reaction is the relief of the ring strain. Remember, 3-membered rings, the bonds in those rings are not very strong. This is pretty much an irreversible reaction. there's our new bond. I'll show that in red. Take 30 seconds to try to figure out where the H comes from. That O minus is going to make a bond to an H. Where does that H come from? Okay, so anybody got a guess? Let me ask this. Is this O minus a strong base? It is, right? It's a localized O minus. Localized O minus on a methoxide is a strong base. Localized O minus on a hydroxide is a strong base. So that localized O minus is a strong base. Do you have any acids in this reaction? What is it? Yeah. So methanol is a weak acid, but it's an acid. So you're going to have the O minus is going to take an H from methanol, and that'll regenerate methoxide. So this is really a catalytic reaction. You can make this reaction happen. You can, if you dissolve the epoxide in methanol, theoretically, if you add 1 molecule of sodium methoxide, this reaction goes to completion. In practice, it wouldn't, I mean, it would do that like over 20 years or something. So you want to add a little more than that. But that's where the H comes from. And that finishes off. Questions about that one? All right, so in case people have missed my announcement or it slipped your mind, there's 2 assignments out right now on Chapter 7. There's a Canvas quiz that's more multiple choice, fill in the blank, that sort of thing. Everything right now is open book, open note. So there's that assignment. I think that's due, that's essentially due first thing Monday. So I don't want to have it due at midnight. If you want to do it at 1 a.m. on like Monday morning, do that. You should get more sleep than that, but that's fine. The other is an assignment you're going to have to actually either print off or write on your computer and turn in as a PDF on Canvas. That's due Wednesday morning. I'll get answers out for that. Other than that, have a nice weekend. Hopefully it warms up. See ya.
Thank you.
You bet.
Hydride carry more than 1 carbon away?
Sorry?
Can a hydride carry more than 1 carbon away?
I got a question. Can a hydride shift more than 1 carbon away? It can't. It can't directly go like 6 away, but it can go 1 at a time. Right? Like a lot of secondary cations, you make the secondary cation, hydride can pop over and make another secondary cation. Like those are equally stable. And so it can just keep doing that until it gets to the most.
Carbocation like 4 ions down?
Yeah.
It wouldn't do it?
Yeah, it won't directly go just pop all the way over.